Okay. So we cover this far. There's a quick tutorial on the really basic. Today we're going to go through PennyLane Fundamentals. It's in this code book. You could register with PennyLane and then you'll be able to access that code book. I can share the screen. Uh, yeah, for example, you go to this page and then, okay, there's a start here. Yeah, if you click, this is the code book. There's a map here. And basically you start from the introduction. After you finish the introduction, you can go any island you want, algorithm, fault tolerance, applications. But this is one that it says a crash course on the basics of PennyLane for quantum practitioners. I hope by now you have become quantum practitioner, as at least you have run quite a few notebooks. So you should regard yourself as a quantum practitioners. Okay. And if you have ever submit jar to real devices, then you are a quantum practitioner. So today we're going to go through all these. So there are four of them, circuit and Q node. Some of these we already introduced the notion, quantum operation as well, measurement, gradient, and optimization. Yeah, so there will be some repetition of what you have learned on Monday, but there will be reinforcement and new uh, operations, functions from built-in from PennyLane. Okay, so the code was uploaded, and so let me see. This is what we have seen last time, Monday. Okay, and this one is the PennyLane fundamental, which I copy some of the codes and my answers. I'm not using the answers. So yeah, but I encourage you to work through some of the code, at least in the introduction, this island in instruction. This island here. Yeah, and if you want to reinforce your learning on algorithms, some of the basic algorithm, you can go to this. There's some basic algorithm. And there's also QFT, one basic mission. We didn't cover much. We all not emphasize much. We have the QFT circuit. We have not emphasized much, but maybe we can come back and show the algorithm, Grover's, right? So this is really basic. You can then learn algorithm from the coding perspective, even if you don't understand quantum mechanics or yeah, but you really only need minimum knowledge of quantum mechanics. Okay, so this is the PennyLane fundamental. Okay, so we talk about device, right? PennyLane need to have a device, and it also has a Q node that you can run. So you import PennyLane as QML. Maybe I already ran this. Okay. You define a device. Usually default qubit and how many wires, how many qubit you want. So here we have 2-qubit circuit. This is the circuit that's going to implement this. Right? There's a toggle bar. Put this into plus, and this is going to have transform 0 to 1. So this input, so this label here, 0, 1, is the labeling of the qubit, now the initial state. Then you have C naught, and you have RY rotation, and then you have followed by measurement. This is the circuit, and the RY has the angle theta. So this is how you implement, like Hadamard on 0, Pauli on 1, C naught on 0 and 1, and RY on qubit 1 with angle phi, and return the state. QML that state, right? As we said, if you have returned anything, then it would put the measurement symbol here. If you only write the circuit itself, this part, then you don't have the you don't have the measurement symbol. Okay, so this defines it. And as we said, if you don't decorate this function with Q node, to run it, you have to assign a Q node to circuit. So this really assigns this circuit is also like assign a circuit to Q node, vice versa. So now you can run that, but run that you need to use this circuit Q node, which is Q node circuit and then the device. So they couple the circuit to device, and that become a Q node. You can draw this, and you can run that. Okay, draw in this with two different way. One is this X. It's hard to see anything. Okay, it's hard to see this. Uh, and therefore I prefer to use this way of drawing. Easier to see the circuit, right? And you can print this circuit output, which return a state. So this is a state, a pure state has 2 qubits, so this return the 4 component vector. And I think PennyLane, the qubit ordering is the same as our convention. It's not the same as Qiskit. This will be qubit 0 and 1, so that this will be the output will be 0, 0, 0, 1, 1, 0, 1. Even the measurement outcome is what we usually use in textbook. Okay, this is another circuit and device. For example, you could have a default qubit, and you can actually name the wires or name the qubit Alice and Bob. I don't know why you want to do that. So for example, here, this one is device qubit, which has name Alice and Bob. So your wire would be, you would need to write theta y equal to Alice. These are x here. And the CNAT wire is from Alice above. But if you write 0 and 1, I think there would be some error. For example, if I write, let's say the R 0, let's see what it would have. It would have error because it does not have the 0. Now you have defined a device that has names on wires. It contain wire not found on device. 0 is not a defined wire because you already defined it to be elephant Bob, so you can only use those. This actually could make programming harder if you all use different names. Yeah, so but the illustrator you could use names. Just like our qubit, we could also in the Qiskit we could also name quantum register, classical register, but in that case you can still use 0 and 1. Okay. And if you need mixed states, then you would need to define the default mix as a device. Okay. We have seen this yesterday about the return the the state, right? There's also returning the probability. You've seen that. Okay. And we also seen the measurement, right? Measurement from yesterday, from Monday. Measurement, return probability, right? And we also see a single shot. That's called sample. We don't need to read. Oops, hello. Yeah. So we're talking about PennyLane. To prepare states, you could actually use the state vector. For example, suppose this is one of the exercise they have. You want to prepare alpha 001, beta 010, gamma 100. Okay. And that's the input. So the three variables. And then what you do is I normalize these value. So they represent a proper amplitude, and the state is this way, right? This is 3-qubit state, so there are 8 components. So the first one is 0, and this is the first component counting from 0. So that's the alpha, and then beta, and gamma is the fourth component counting from 0. So this 4, and then 5, 6, 7, right? And you have to specify the vector. There's a function on PennyLane that you can actually prepare the state. We call QML.statePrep, and you can actually prepare that, and you need to specify the wire range. So from 0 to 2, these are the 3 qubits. So we can take a look at this. So there may be more. You see there's also arbitrary state preparation. Prepare a subsystem using the given vector in the computational basis. Okay, stay wire path 1. You could probably path with 0. Okay. By setting path width to a real or complex number, state is automatically packed to dimension 2 to the n, where, okay, the number of qubits is complete. Okay, so if state preparation is not supported natively on the target device, PennyLane will attempt to decompose the operation using the method declared by Moulton et al. There's also another function, Moulton state preparation. You prepare the state and you can evaluate this. So there are more in the document, very interesting. You can differentiating with respect to the state. Okay, but the state argument is in general not differentiable. Okay, non-trivial classical. Okay, so this is not possible. You cannot differentiate respect to the state. Generalization. So we need to normalize us. Okay. One can set normalize equal true to automatically normalize. Okay. So what we can do is copy this. So this, maybe I just, oh, X, actually close it. Okay, so here we can directly use alpha beta without normalization, but then we have to use. Let me put comment here set to automatically normalize. Okay, this is from the code exercise. So that's I ask you to write the code. So what I could do maybe open the code book. Yeah, you came in later, but Monday we talk about PennyLane, and they have a very useful code book where they have a lot of exercise for you to work through. And I'm going through this. So yeah, this is the circuit. Complete the circuit, right? This is very easy for you. We have done that. Okay, so that's all, and then you can compare with the solution. I don't want to show that here. And they talk about the device. Yeah, this is their code, and this is my code. Okay. Okay, so yeah, this is the circuit. People keep it and use it to know this is what we already did. Right? So we will do this. And then they also say, this is called, we define the circuit, a circuit one, so circuit two. So I may not necessarily go through all the exercise, right? Okay, but it's there if you want. Yeah, they also mention another molten state operation. We can also check QML molten. Right. Yeah, there's also another one. How do you pronounce it? Molten state. Okay. Create any operations on the right. So this will be similar to the other one. This will be similar to state prep here. Okay. So we implement this. This is a two parallel qubit. And yeah, the code. I think that's the code exercise up there. Yeah, so this is really easy, right? For you guys now, it's like you can close your eye, you can even type it. Adama T R X and Hadama S R Z with angle phi. Okay, the RX has angle theta. And then return the state and we output the state as a vector. Okay. Then maybe more interesting is the multiple qubit gate. Okay, I'll go back to here. Not going to spoil much. Actually, we should spoil uh, going through all these exercises. Okay. Sub-circuit one is already there. I probably didn't go through this. I don't need that. So the next, if you go next, I thought it has these next you can click view modules. I think maybe we're here. Uh, oh yeah, here's next. Okay. This is what we went through here. And then the multiple qubit gate, and ask you to really just implement this. This is control RY, control RX, and they have a built-in the CRX, CRY here. But here we have 3 qubit, so we define a device which is default.qubit and wire equal to 3. There are 3 wire, 3 qubit, and you decorate the function with this Q node, so you can run it. So this is really easy, just Padma. But this one you have used control RY. This is the rotation angle, phi, and then what's the wires? 0. As control 1 is the target. Next is RX, CRX, control from 1, target is 2, and the angle is theta, right? ST gate, you know how to write. The 3 qubit, this is Toffoli gate. So Toffoli, you need to write what are the qubit that are control. So 0, 1 is are the control, and 2 is the target. And then you have the swap. So swapping 0 and 2. So yeah, so this is example of the 2 angles. And the output the state, and then I draw the circuit. And just write this as big AX equal to that. And in PennyLane, you can also define gate or control gate using a matrix. So this is the next one. It has a matrix as input. So this is actually the next exercise. I think I skipped this. Probably I skipped this. So this one, maybe I just mentioned that this one is control using 0. So what you can do is, I didn't write in my notebook there. You could say control value equal to 0. And you can turn any gate into a control gate. So for example, you just need to use QML.control, and this is the gate, and 1 is the target, but 1 is the control. The control value is 0, and this is acting on 2, qubit 2. And here is a phase kickback, and phase kickback we learned that in first in Deutsch algorithm. But here it's just provided as a matrix. Okay, this is a matrix, 2 by 2 matrix. Apply phase kickback to a single qubit operator whose matrix is norm. Okay. So what you can do is using this function. So because you want to do the control unitary, so you use this function QML.control qubit unitary. This is a matrix, and specify the control wires, and that's the target. So let's take a look at this. Maybe there's more interesting information. Yeah, control wires, control value. So you can always set control value to 0 if like using instead of 1. Yeah, so this is you have 2 by 2 a matrix, and use control qubit unitary U and control wire 0, 1 wire equal to 2. Okay, wait. This is 2 by 2. Find a single unit apply to wire 2 control on both. I see. This is, you could have control on both wires. Okay, you have 3 qubit and single. Yeah, so this is a single unitary, but then you have 2 control. The control U. Then you can also specify control values. It may be the first qubit you want to use 0 as a control, and second qubit you want to use 1. You can actually specify using the control values. Let's see if they have example. Control value right here. Control value, you could use 0, 1, 1, right? So this is using qubit, the first qubit 0, second is 1, and third is 1. Yeah. So you can actually, it's very flexible. Right. In Qiskit, perhaps to do that, you will need to write your own, and yeah. So we do that here. Right. Yeah, having look at the document, and it's pretty easy. I could just say control values. Okay, still 1, but it doesn't change anything. But you could have it value being 0, then you would have different state. So this is, for example, this 0.15. If we control with 0, it's still the same. Maybe the last one. Okay, last one is minus 0.24. It's plus 0.24. So there's a yeah, the second qubit has different value, right? As depending on what the control. They also have next is a multiple qubit gate, but you have these XX. So that's their next code exercise. Okay, yeah, I have this here. This is they want to consider this kind of pattern. You apply V, control U, and then V dagger to undo the V operation. And here they want to use Ising XX. Okay, so yeah, so I have the code there, okay, but also here. And this is just to the preparation, state preparation K. It prepare 1K on wire 0. Okay, let me take a look at circuit. Let's prepare that. And here we say no, normalize true, so we don't need to do that by hand. And you apply theta is to define as Ising XX. So it's applying e to the I XX times angle to wire 1 and 2. Okay. This is to apply this. But in this diagram, it's a control. So we'll need to turn that into control using QML dot control, and this is Ising angle wire, and then this is control. Okay, and let's take a look at these Ising. So you have to be careful about whether the definition is phi or phi over 2, right? Like in our rotation, we usually use poly over 2 because that's the generator of the rotation. Here they use this convention. So xx and then phi over 2 and there's a minus sign. Some function, they may not define a minus sign here. They may not use a minus sign. So you have to look up the definition. Okay. Right. And remember we talk about this parameter shift rule. The derivative of this gate or any function of these, it's evaluated at phi plus pi over 2 minus the value at phi minus pi over 2 and divided by 2. So this allows you to do the derivative without actually calculating the numerical derivative. So this is exact. Okay, so there's that of this feature. Okay, having understand this, then let's go back to our circuit. So we do the V and then undo it with V dagger. So this I define apply Ising XX. So I combine it here. So first I do the preparation, do K here. This K is just a number and this 1K, the wave in the 1 qubit, and theta is the angle that I want to rotate in the Ising XX. Okay. So then you output that. So let me just run this. One thing just to emphasize again is because the control, you want to use the control. So you will need to do this. QML that control. It turn any gate into a control gate as we've seen. So let's take a look at this. Control values, right? Work wire. Work wire, any auxiliary wire that can be used in the decomposition. There's something interesting. This device is lightning that qubit. I don't know what this is. Okay. Here you see there's some workflow of condition. If you have some condition, classical condition, you can do some rotation, for example, that we talked about yesterday, not Monday, in classical. I think I have that toward the end. Mid circuit. So I have this mid circuit. I perform the measurement, give it one, and depending on the outcome of this M0, I do RY here. Okay. This is measurement probability. We already see that. So apply V, control U, and then inverse that, and then you return the state. Okay. So I do 2K and then do the control Ising and then do the adjoint. This is already here. Okay. And then, but the difference is we just returning probability. Okay. But this is from this code exercise. The next one. So I think we gone through the second part. So once we have gone through this, that's the crash course for quantum practitioner. Okay, so samples. Samples. We talk about sample also on Monday. it simulates that the machine is running and then shot by shot. Okay. So here I define a device. D for the qubit wire equals 3, so 3 wires, and only have 3 shots. So this is different from IBM Qiskit. It define a device with shots. But in the IBM Qiskit, when you submit to a simulator or a device, and then you specify the shot, the device is there, and then you submit saying how many shots you want. But here you create a device and only give you how many shots. So okay, so this is the same as the previous one. Um, okay, so this is the previous one, the same circuit, but it does the shot. And so you return. So when you want to do the shot, you need to say sample. You return QM.sample, and the shot according to which wire. So wire 0, 1, 2, it would give you all the 3. But if you only want like qubit 2, then you just say wire equal to 2. Okay. So when you run this, it would give you the 3 shots and what's the output. So 0, oh, here is 0, 0, right? So this one is the qubit 0, qubit 1, qubit 2. So that's our usual convention, not the IBM convention. If you run again, you would get different results because it's simulating the sampling of that. Okay. Next is the expectation value observable. So we know from last time, you just say, I want to return QML.x exp value, expectation value, and the operator, you can specify operator. Yeah, so here you can specify any Hermitian operator. So here, this is really poly Z, but you could specify other operator. And then, so this is very flexible. You can define any Hermitian operator using matrix. In Qiskit, we have this operator class, and you can also define. And we can also using the poly, etc., right, to decompose. Okay, so here, the thing that we learned here is you can have a matrix, that say I want to, oh, I think this shouldn't be matrix A, it should be just A, because I'm using A here, or maybe I will change that to matrix A. Okay, so you need to change the code on your end. Okay, so we can draw that and then print the output. So it will print the expectation value of this matrix is the answer of this that it returned. So for example, we can change the matrix. So you could change the matrix A. Right, if you want, you can change the matrix A to any 2 by 2 Hermitian operator. For example, we can change this to 1J sigma and then 1J. So this will be, I add another sigma Y, so it's sigma Z plus sigma Y. And let's see, yeah, and that's the expectation value is 0. 0. What about I put sigma X? It's also zero. Maybe it's because of this. This is because okay, this because okay, this is because you are evaluating a single operator, right? So and this is a failed state, and you create this is completely mixed state. So any poly operator would be is evaluated to zero. So we add identity, then it evaluate to one. Okay. Any questions at this point? Anyone from Zoom have a question? Okay. Okay. So next is tensor product of observable. Okay. So here is to evaluate poly tensor product poly zero tensor product poly one. And this is the same circuit. Like we know this create a Bell state. The state is 0, 0, 0, 0 plus 1, 1. Of course, normalized. So ZZ is a stabilizer. So when you evaluate this, will be 1. I think we have something similar in the last notebook. And then we have these gradients. I took the picture from PennyLane. Okay, but this is here. So we're moving to the next. This is actually moving to the next code exercise. It has a few parts. It has a few parts. I think it has 5 or 6 parts, including the sub exercise. Yeah, so this is the circuit. So this exercise wants us to implement the circuit shown here and return the expectation value of Z0, meaning the expectation on this qubit. Okay, and there are 4 parameters. So the circuit is Rx theta 0, and then control not, then control not from 1 to 2, control not from 2 to 0, and the 3 rotations are Y, theta 1, theta 2, theta 3, and 0, 1, 2. Yeah. Then you return the expectation value, poly Z on Y or 0. Okay. So there are some values here, so maybe I should print. Okay, so these are the angles. And maybe I print output values. Output value. Okay, yeah. These are a list of angle I think would be useful to make a plot. It'll be useful to make a plot. Should we do that? Should we make a plot? Okay, maybe we make a plot. I don't know, we import network. Don't, maybe we need to import it. No. PennyLane may have its own plot function. Visualize circuit. Probably not. We'll probably import our own. Oh, there's some code. This is circuit. This is just circuit. Oh, this is just. So let's use this plot. What would be its? Who knows how to plot this? Import. Okay, let's import this and then plot XY. Okay, we have these data here, so let's import this and this is this like this and XY. Okay, simple. X is angle alpha and then Y is alpha value. How do we add a legend or add the X, Y axes and anything like that? Do they have examples? Text label. These labels. Okay, let's copy. Now AI is very useful. Angles. And then this will be Z0. Title. Okay, 3-qubit circuit measurement. Beta series. No, just the expectation value. Yeah, if you have an example of plot in your notebook, then next time you just need to copy. Okay, cool, right? I think in there here, if you submit the answer, they will plot it for you. Let me just submit this part. You think? Yeah, they did that for you. Okay. Then here is strong entangler. So here has 4 qubit, and I don't see why it's strong entangle. But they named this strong entangler, and you need to apply the circuit. They call this strongly entangled layer. Okay. So you do this by hand. Is the next is this? Oh, see. this part, you could do this on your own. Yeah, you could implement this on your own, right? Rotation on X. This, I'm trying, maybe I copy this. So this next part, you need to implement this circuit, and you can do it by hand. Let me just say, implement the following circuit by hand, or use PennyLane strongly entangling layer. Okay. So we could do this, but if we do this by hand, we need to know the rotation. I think UML that rotate, maybe this is the function. Yeah, UML rotation, right? Phi, theta, and omega. We will need to use that. This is from this. Yeah, I think this is from, for example, Euler decomposition. Okay, let me just write it here. By hand. Okay. So if we were to do it by hand, then we use QML dot rot, and then alpha 0, beta 0, gamma on wire 1 on wire 0, and this one alpha 1, beta 1, gamma 1 on wire 1, and this on wire 2 and wire 3. Then you use right control not, control not, control not, and then control not back from 3 to 0. Okay. But they have these strongly entangling layer, and you need to input the weights. So for example, these are the weights. Four set of weight, each have 3. Okay. And that's the input and the wire range. Okay. So that's it. And then when you print out, and it will say strong entangling layers. Doesn't show you the detail. So, but we can take a look of this function. Okay. Strongly entangling layer. And they have a few options. So for example, this is the one that we've seen, but you could also reverse this, or this from 0 to 2, 1 to 3. This one is 3 to 0, and then this one is 4 to 1. You could also skip that, right? So there's another parameter, R, the range. Range is so this is range 1. So I think this is useful parameters. Range drop level divide. Wait. Okay, so let's draw that circuit. I wonder why it can't draw this detail here, where here I didn't see any of the detail. Print this circuit, use strong entangler, strong entangler. Weights is not defined. Oh, test weight. Somehow we can draw this. This is nice. Oh, I see. So maybe that when they draw and says level equal to device, it will show the detail. You don't show the device. It won't see the detail. Suppose I do not have this. They only see the bare level. So this option is useful. Use level device. Up here. Okay. And you can also, right? You can also use range R, ranges R, ranges equal. It does not. Okay. Ranges. So maybe let me put this level equal to device. And let's put ranges equal to, is it one? We'll have this. Okay, if we say two, then this one will be connected to that one. Right. Would have range 3. Let's see if we use range 4, what would happen? It probably cannot do the control itself, right? If we use range 4, then it would have error. Okay. Of course, you probably wouldn't. Range 5. Oh, you could have range 5, but it's just mod 4. Okay. So here we use range 1. Okay. So that. So you play with this parameter and see how the function works. Okay. Here we are sort of toward the end of this, and now you almost done. So how you embed a feature, right? So when we haven't talked about quantum machine learning, but in classical machine learning, you would need to embed the feature, especially in quantum. How do you make the classical to quantum? So they have these embedding feature in they have something built in, I guess. So they use this angle embedding routine. Let's take a look at this. Yeah, I think learning is a different platform. You just need to go through the documentation very often. QML that angle embedding. So it embed the parameter, like maybe from machine learning data, you embed into angle. And you can here you can say what kind of angle you want. So here feature equal to feature vector. This will be the input vector, I guess. Rotation wires, and then yeah, wires, and then rotation is Z. So you have 1, 2, 3, you embed that. So when you see that rotation, the angles here. Yeah. Okay, so let's see what it asks us to do is yeah, this would bring the okay, this is to embed a feature. This particular code, okay, so this particular code is embedding the feature, and then there's also a parameter. So in quantum machine learning, they are usually the classical input that are the features, and there's also the variational circuit, and associated with that are these variational parameter. So the feature will be something you take it to training, to train, and then the parameter is your neural network, right? This will be your neural network with parameter weights, etc. But it's not exactly the same as the classical neural network. And then depending on what you want, right? Here we want to optimize the Z0 operator. Right? But maybe let me add this code block, the feature, before we do that code exercise. Yeah, that feature. This one here. So we're going to draw this. QML, UPL, MPL. Yeah. Okay. So this will be the three angles. 1, 2, 3 will be here. Okay. Here we don't have any variational circuit, but here we are doing only the feature now. So this is embedding circuit. Right, your code. Let me see. This is drawing something different. So embedding feature. Actually here we have a few other things. So here is this embedding feature using angle embedding, right? And then I have, according to this circuit there, I have then rotation at the end. Yeah, so that this code block was to implement that. So let me draw this. Let me draw this. UML.draw MPL. I'm going to draw embedding circuit. I think it's level equal to device. Okay, so we draw this, and here I'm using a built-in function. It's called QML.Jacobian, which we introduced last time, and allow us to evaluate Jacobian. And this is just drawing the circuit, the Jacobian circuit. Maybe we also use the level equal to divide and see what it's doing. Warning, when the input to QML draw is not a Q node, the level argument is ignored. Okay. Okay, this is not because QML, the Jacobian is not a Q node. This embedding circuit is a Q node. Okay, so it's ignored. So maybe let me just drop this draw. So this here Jacobian allow you to get the Jacobian of this function. The function meaning that the z expectation value as a function of the free parameter, right? And here, when I input a feature, I said that the gradient is false. I don't need gradient for the feature, but I want the parameter to have gradient. Yeah, this is this code exercise. Okay. How many components do you expect this gradient to have? Okay, so let me ask the question. So how many components do you expect the gradient to have? This Jacobian would output what? What is Jacobian? Jacobian is take a function and take the derivative, second derivative, theta I, theta j. So you have three angle, you have, so that should be 9. 9, 3 plus, 3 times 3. Why do I only have this way? The gradient of the circuit is, we have 3 parameters. Let's take a look at this. Let's take out the definitions of this. Return the Jacobian as a following function. Yeah, what is shape 4213? Is a single with shape 2-1. Output probably of each 2 wire cables. The Jacobian panel will be a single array with shape. This, two. So the Jacobian is only taking the single derivative. Is Jacobian only taking single? What? Only respect to that one parameter. So maybe, yeah, the Haitian is the second derivative. Jacobian is just gradient. So it should be the same dimension, yeah. Yeah, okay. So the last time we also had this. Yeah, okay, that Jacobian. Oh, I see. That's the last time we used Jacobian. We use it twice. That's why we get the same as the Haitian. So when it use this Jacobian, it's really using the auto differentiation. It's using this to calculate. It does not use the parameter shift. So if you want to use the parameter shift, you would have to choose a different function. Here when we use Haitian, we use parameter shift Haitian, gradient parameter shift Haitian. So, but I want to see if there's the gradient has other, yeah, parameter shift. You could have parameter shift Haitian. What's CV? Just call continuous variable. Parameter shift. Fine, I did. So it has a few different functions you can use. Gradient transform. Okay, yeah. So now, yeah, this is the gradient. So Jacobian, maybe we should just call it gradient. Gradient is probably because usually when we talk about Jacobian, it's a transformation between the two different variable, the different set of variable. We're doing the change of variable, and that's you take the respect the new one respect to the old one. So it's actually a matrix, but here is the what it means is gradient. Okay, so this is close to the end. Okay, differentiate gradient and Jacobian. There are more, but that's probably all almost. Maybe this we can take a look at the problem description here because I did not copy everything or the diagram. Okay, so write circuit for Asian. So with this circuit, so this circuit we've seen something similar, and there are four parameters, and return the expectation now is it's as Z0 cross Z1. The QNO should be set to be differentiated with parameter shift method a maximum of 2 times. Oh, see. Yeah. Okay, this is my answer. So this is implementing the circuit is easy. Implement the circuit, we have seen the icing, Rx rotation, and here keep it 0, keep it 1, and then you return poly 0 at poly 1. And there are 4 parameters, so the test, these are code that they already have. You just need to here. So you apply 2 solutions. Okay, one use the parameter shift. That's what we saw last time, gradients, parameter shift, Haitian. And then you get a Haitian. Okay, this put it into array. Yeah, this is the other solution using Jacobian. So yeah, this is what I wrote. I think test. Yeah. So there are 2 different ways of doing that. Is you take the derivative twice. But I don't know this Jacobian. It looks right. We look up. It says it's using JIT. Return the Jacobian column function vector values. You know this function compatible with us. It's compatible with that autograded QJIT. Ah, that is parameter shift and a join on internal queue node. I'm not supposed to put order. Okay. Yeah, so there are more information here. Yeah, this is somehow very interesting. You can use here that QJIT. So you can really do all this machine learning and with this quantum circuit. Okay, so let me execute this. So in notation, there are 4 parameters, so it'd be 4 by 4 matrix here. Evaluate at that point here. Okay, so the next, let's see, the next is you ask you to define a cost function. So you have this expectation value, but you may not necessarily just using this value, but you want to optimize some function. So for example, it's optimizing this f of x, xq minus 1/2 x squared plus x. You want to optimize this function. This will be your cost. Okay, so this is really just writing the cost. Yeah, so this is writing the cost. Reason this it may seem odd. This is the function value cost function. This is given. And what it's doing next is allow you to use optimizer to really optimize the values. So this is the next. So we have this functions, right? Cost function, and we can use optimize, which take the cost functions input and initial parameter and add a number of steps to optimize a cost function. Okay. So this is the optimized function that's they write. So let me just maybe it's okay. I've just used they wrote this. So this using optimizer using this gradient descent optimizer, and this specify the time the step. You could also take a look at this, but let's just go through the structure. So this initialize, and then how many total step you want. For each you do the step, you just say optimize that step. Then the parameter would update. And then once it's toward the end, at the end, then you just return the optimizer, return the function, the cost. Okay, so this is the test. So let me going to run on my side here. So this is initial parameter set, and you will need to say requires spread is true. Okay. And okay, so I can return, for example, this minimum value, or should also maybe get a optimize parameter. Print minimum. Okay, I'm just looking here. I was looking at what is the type of the minimum. It's give you a tensor, so it give you something that you can do the gradient or differentiation. Optimize parameter. Okay, so we toward the end. This is actually the last line. of the code. So it's optimizing, right? So this is optimized is minus 2.5 roughly, and this is optimized further. I wonder whether we could get the intermediate. Like in Qiskit, we've seen that you could have intermediate values and we plot how it converges. But I have not gone to that stage yet. So maybe this will be a question that you can think about how to get the intermediate value. Maybe I put it here. Okay, let me put it here. Oh, to extract. So we'll need to use callback, some kind of callback. Yeah. Okay, so that's the end of this. So maybe next week we can start presenting the lab